We're going to go ahead and get started. First up, I'd like to call up Nick Holt from Microsoft. He'll be giving a talk on addressing challenges in an Anycast CDN.
Okay, good morning. Yeah, thanks, Steve. I don't see so much staggering. I think you were off there. People are just getting up slowly. So hi, I am Nick Holt from Microsoft. I work in the Azure networking team. My larger team I'm part of is responsible for Microsoft's overall backbone network, 8075, a global network appearing all over the world. And in addition, proxy and content services to help speed up the application performance. That's what I'm going to talk about today. And FastRoute was a paper that a bunch of us put together, led by Ashley Flavel, a great guy from Australia, who is no longer with the company, so he was kind enough to lend me all his slides. Okay, and I'm going to push the green button. Oh, fabulous. So let me give you an overview of what I'll talk about today. So FastRoute was designed to help us with our load management. Most online services today exist in a small set of data centers. It used to be the case you had a web server with the content on it delivering an HTML page. Now all major websites, you're coming back to a data center to get specific information, ad placement, whatever, for that user. And there's thousands of machines doing that, so you can't get that same stamp all over the world. So the set of content we're looking at is going to be in a few places. To that, you add a set of edge nodes. You can put edge nodes anywhere on the internet, peering points, deep in ISPs, and in our data centers. We have them spread everywhere. And the goal of those edge nodes is to reduce the latency of the services, mainly through proxying the traffic. I have a couple of slides. I'll explain how we're going about that. FastRoute will be the last section of the talk. That's the mechanism we use to manage load. So in the best case with Anycast, you have sufficient server capacity wherever the users organically land, and their traffic just goes there. But there can be issues with swarming, organic growth, and so we needed a load management system, and that's what I'm going to talk about. And I put the note at the bottom, traffic routing in FastRoute relies on Anycast, so you can all prep your Anycast hard questions to hit me with at the end. That's the part I'm looking forward to. So the talk's three parts: why use an edge, choosing the best one, and then what FastRoute adds on top of that. So why use an edge? So as you can tell, this example was by my colleague Ashley, so it deals with a very important user in Australia. And so we're assuming the service they're trying to connect to is hosted in the US. If you look at the round trip time from a user in Australia, either over our backbone or over the internet, it's about 180 milliseconds to get to the US. And so to get the TCP connection, you got one round trip. The first byte of the response, you've got a second round trip. If your content's over SSL, which increasingly it is these days, you've got another 2 round trips for that handshake negotiation. So you end up with, doing the math, it says here, I'm glad I wrote that down, 720 milliseconds for an SSL first byte comes back to you. And with modern apps, we started off working on Bing at Microsoft when we did this project. The page load time goal is sub 1 second at the 90th percentile of the internet. So we lose if we do this. So how does an edge help? So if you add in the edge, the client will connect to the closest edge. Next section of the talk is how you find the closest edge. And let's assume their round trip time is a lot better, say in the 30 millisecond range. Your initial handshake, TCP connect, SSL setup, GET request is now over that tiny round trip time. So you've got 4 times 20 milliseconds. And then it takes 1 round trip time, we assume, from that edge site back to the main data center to get the content. There are a couple of assumptions in there. One is this is going to be over a hot TCP connection, or you could use your own protocol, forward error correction, anything you like. But in general, for these connections, which are across our backbone network over previously warmed connections, it's 1 round trip time to go get the content. And obviously on the back end, there's some time for the data center to figure out what the answer is, what the search result is, or which piece of email you want. So the math there is 4 times the 20 plus 1 times the 170. Now you're at 250 milliseconds. So we basically halved the time to get that first byte of the page to the user. So significant improvement. This is called split TCP, this principle overall. Didn't invent this, we just read about it. That's only the start of the story, right? Because if your page weight is 30, 40K, if it has multiple URLs in there, all of that stacks on to the download time. And all of it can be accelerated. Any TCP packet drops, retransmits are now within that short 20 millisecond loop, and that really helps with a slow start, et cetera. So that's why we believe in the proxies. And I talk of them as proxies. They're also doing caching. So if the content that is being proxied has a TTL on it, it'll hold it there and deliver it. So that's the closest we are to a CDN. I wouldn't say we're a CDN. We are a proxy service that can cache static assets. So the next section is, how do I direct the user to the closest edge? The classic answer is map the internet, and then we prefer the Anycast. So I'm going to do that one second and say it's better, but everyone can have their own opinion on this. So with the map the internet approach, say you have, here's our example, you have 4 data centers around the world. Let's call them A, B, C, and D, creative naming, and a set of distributed users. And what you want to do is figure out how to get each user to the closest data center to them, because that will give them the best performance. So the first thing you have to do is go out and ping the internet or run a flight that gathers data from your customers to say, okay, the customer that used this DNS server went to this HTTP endpoint. You can do that by doing a flight with GUIDs on the URLs and joining the data many different ways. But you basically come up with some giant set of data that is your map calculator. You feed the output of that into your DNS system, and then when any client comes to ask for the address of your service, your DNS system says, okay, like magic, the people in Asia will go to data center C. Pretty common approach. And the one case I want to look at here is, say one of your data centers goes offline, like the Australia one. You have to have some kind of endpoint health monitoring from your DNS system, so it realizes it needs to give out a different answer, because the set of people who you've given out the answer to the data center in Australia can no longer get there, so they're having like a short service outage. Once you've decided to change the answer you give, you then have to wait for DNS TTLs to expire, and you have to wait for the application to give up. And Windows, unfortunately, hangs on to these DNS records for quite a while. But once that's happened, your DNS system, your big brain in the center of the whole thing, can give out a better answer. There's a couple of benefits from doing this. The primary one is control. You can ultimately take any user to any server, and this is really handy, particularly when you have load and you're trying to move traffic around based on load. We're more focused on the performance side, so that's why I'll talk about Anycast next, why we lean in that direction. Trade-offs, there's a high cost and complexity to this central DNS system. You have to have regular map builders running, gathering that data. Any change in BGP on the internet will invalidate your map. There's some length of time before you found out about that change and you update the map to give out the new answers. DNS can be inaccurate. This is also a commonly known problem, and eDNS is one of the answers to it, that you're not getting a call from the client to ask which is the server closest to them. You're getting a call from the client's DNS server. So the IP address you're doing the information selection on is actually of their DNS server. And for availability, it's quite common for a provider to have 2 geographically separate DNS servers. So for example, at home in Seattle on my local ISP, the DNS servers when we did this experiment one was in Phoenix, Arizona, and one was in Portland, Oregon. And I'm in Seattle. So the closest you can get to naming me through DNS is that I'm somewhere between those 2 spots. And then availability, as I say, one of the key factors when a site goes down, you have to change your answer, is the length of the TTL. You would have to wait for those TTLs to expire. So this drives people to use relatively short TTLs on unicast answers, and that causes a lot of DNS lookups. And we looked probably 2 years ago now, and the 75th percentile for DNS lookup time was between 50 and 80 milliseconds. So again, I guess coming from the Bing side, you're totally perf-centric. Those are key times to get rid of. So as Ashley writes here, there is an alternative, and that's Anycast. So how do we do the same problem in Anycast? So same 4 data centers. This time, instead of giving out a different IP address from each, they all announce exactly the same IP address. There's code in the servers in the data center. If they're unhealthy, they pull their route. So any healthy edge location is going to be announcing the same Anycast IPs. The DNS system is trivial at this point. Whatever your question, The answer is the same IP address. So relatively little code in there, it helps perform really quickly, and it gets rid of the whole giant table creation phase. So essentially lazy, we'll just give it the same answer to everybody. And then by the magic of the internet, as they like to say, the right users are connected to the right data centers. And this isn't 100%. There's a lot of work that goes into this, but it moves the performance problem from being that of table generation and figuring out and algorithms into a more steady-paced big data problem where you look at the set of people coming to an edge, you say, are they geographically close to this edge? If not, break it down, which ASNs are not coming here, and go talk to those, pick up the phone, talk to people, say, hey, we'd like to peer with you. Your customers would benefit bringing in the traffic more locally. Again, if Australia goes out, this is one of the things people worry about Anycast. What if a data center goes down? Well, actually, it makes no difference. Any in-flight TCP sessions will be broken. What will happen is the client will receive the data that it had already requested because the session is fine. When it ACKs that data, the ACK will land on a different server in a different data center who has no idea about this TCP stream. So the key thing to do is immediately reset that connection so the client isn't left hanging. And then you rely on either HTTP level to retransmit or the user to push F5 and try again. But there is, any in-flight sessions will be broken. Any new ones, if they get the reset and retry, they'll immediately start a new connection with a brand new server. So Australia's gone down. All the users that were going there get resets. They immediately try to reconnect, and they will find the next closest server. In this case, most of them probably would go to Asia, but it could be that for a particular ISP, if you're in Brisbane, the west coast of the US is closer. So the traffic will organically go to the closest place. Because that's one of my themes, is that the traffic just goes where it's supposed to, and we have to deal with that, versus trying to be in control and direct where it goes. So benefits, we think of this. It's simple, it's highly performant, so we're going to serve the request from the point at which your traffic entered our network. And that is the best we can do. It avoids the DNS correlation issues. It doesn't matter which DNS server IP you came with, because whoever you were, I gave you the same answer. So the clients are all getting the same IP address, and then now from the client machine, it is taking the fastest path versus a path that was determined based on what their DNS server was. And it reacts very quickly to changes, even with a long TTL on the DNS answer, because the answer itself is high availability. If a server goes down, it'll go to a different location. We're able to just let the BGP on the internet direct traffic around. A trade-off, I love Ashley's line here, so it relinquishes control to the internet, which fortunately is not that scary a thing. But it does mean that you're subject to where the traffic comes in, and you have to deal with that, and that's what the third part of the talk here is about. The FastRoute is how we worked out how to deal with that. Another interesting point, you have to size your POPs, your edge locations, based on organic traffic volume. So if you put a node at an IXP with relatively little peering, it won't get much traffic. As you pick up peers there over time, the traffic grows. So there's a fairly tricky capacity planning, which we've had a few attempts at, to determine how do you size each site based on the traffic that's coming in. And our canonical challenge actually was Miami. We looked at the traffic coming into Miami, ton of traffic comes into Miami, put a lot of servers there, that's gonna be good. And then we got peering in several places in Latin America, all the traffic went away. So now I have a lot of servers in Miami, if anybody wants some, and not much traffic coming there. So you do have to try and predict as the internet topology changes where the traffic's gonna be. And the third one is the possibility of overload. Cue the next slide. So FastRoute is our load management system. We want it to be simple, highly available, high performance. Doesn't everybody of every service. And so what we were looking for was a solution that was as simple as Anycast, but had enough control to handle the overload. So we didn't want to get in the way of Anycast for the high performance routing. If a node was able to take all the traffic, it should get all the traffic. But say there's a gradual traffic ramp during the diurnal in the day, and it starts to get a little too much traffic. You want to still serve as much as you can from that location, but take, say, the top percent, maybe 10%, and move it somewhere else. How do you move it somewhere else? Where do you move it to, were the questions. So let me describe what's behind our model, and then I'll say how it works. So as I realize it's been great talking to people here. Everybody has a different internet in their head because it depends where you stand looking at it. So from where I stand looking at the internet, we have this giant backbone global network. And some spots on it are really strong. So we have giant data centers. You can host any service there. You can put it in Azure. You could do the same in AWS. But there are places on the internet that are super strong. So those we have as red, we call those data center edges. Essentially infinite capacity for this proxy level traffic, but quite a ways from the user. So maybe these are 100, 150 milliseconds away from the 75th percentile of users. The next step up, I've called these backbone edges. They don't have to be on your backbone. They are in our case. So these would be at strong internet exchanges. So 1 Wilshire, 1/118th, the Western Seattle, wherever there's a lot of traffic that you can peer with in one place, it's worth putting a larger stamp. So these will be, so the data centers are like, tens of thousands of machines. Backbone edge is probably in the 2 to 5 rack range, something like that, depending on how much traffic. Again, organically sized per location based on the traffic volume. And then the last set is the reach edges. These are the exciting ones, right? These get as close to the customer as they can. In Ashley's diagram of his mom's distance from an edge, we can get this down to 20, 10, as few milliseconds as we can, depending on the carrier technology. So that's where we really want the traffic. That is the shortest round trip time to the user, which based on the math earlier on gives us the largest overall gain. But they are necessarily fragile, they're smaller, they're less reliable. So you have to have a way to move traffic up and down. Here's the same thing drawn on a map. Big data centers, probably 3, maybe I think Azure's up to 20 different places now. You could go for a big data center. The yellow ones would be these larger peering points where a lot of traffic comes. Maybe you pick up a good transit carrier there, get a lot of traffic. And then the green edges are as far and as deep in the network as we can. How do we manage traffic across this whole set? Oh, I should have said on the previous slide, there's 3 IP addresses. The first IP address, IPA, is announced from every edge we have, whether it's a reach, a backbone, or a data center. So whichever, as the client comes in, it will come to whichever the closest server to it is. And then we have another IP address that DNS could choose to give out that has only the backbones and the data centers. So if you start giving out that IP address, the clients can see all of the big edges, but they can't see the little tiny ones. Basically, the technique is, if I can't handle the traffic, throw it to the big guy that stood right behind me. I don't care which big guy, I'm not able to direct to them. I just say, I am getting overloaded, help, somebody bigger behind me, help. And that happens at each level. If the backbone edges are overloaded, they do the same. So here's that in slides. Your problem is an individual edge, right out at the edge, is getting too hot. And what you want to do is shave a small percentage of that traffic, the overload amount, and give it to people in the yellow ring. And the key point here is there's no interaction between edges. There's no global state required. Each edge can make its own decision. I'm getting too hot. I need to get rid of a bit of traffic. The same thing can happen at the yellow layer. If one of those gets too hot, it starts giving out the IP address that only has the red in it. And that's done through CNAME chaining. In order for a node in the yellow ring to be able to shed, it has to be handling that DNS request because we tie the two together in DNS. I'll do that in a couple of slides. And in order for that DNS request to come, the NS records for the DNS have to be in the same ring. Otherwise, what happened the first time we did it is the traffic came to the green ring, through to the next layer, but it recursed within the local DNS server and gave out the wrong answer. So I can give people more horror stories afterwards if they're interested. So how do you throw the traffic? Key part. So what we've done is we've co-located the DNS servers with the HTTP proxies. So every edge, your DNS request is going to land on the same edge that is going to serve the traffic. We have a feedback loop on the DNS servers that they monitor the HTTP service. So if load is getting too high on the edge overall, then DNS is able to respond to that and simply give out a different answer. And we've tuned this over time. It was great. We started just with CPU load because that was our key metric. And then as we improved the software, we could do more for the same CPU. The NIC started to get hot, so we added shedding on that. And then the top of rack uplinks would start to get hot, so we shedded on that. So we sort of gradually worked our way out of the network. My favorite shed at the moment is if there's too much power consumed in the rack, we start to give traffic to somebody else. And there was just one location we have a rack that was very power constrained that we added that for. So you can build any number of metrics that you care about that you require to move load. So the DNS system, you come to the DNS server. If it's running too hot, by any definition of hot, it starts to give out probabilistically a CNAME to the next layer. So there's, again, no knowledge of the entire system. It's just saying, OK, I'm getting really hot. Instead of giving out an IP address that comes to me, I'm going to give out an IP address that comes to those big guys right behind me. So yeah, preserves the independence of the nodes. So there is a key assumption in here, should come clean on, which is that the DNS request is landing on the same place that the HTTP request is going to land. And there's good correlation here, but it's not guaranteed. So in the example I gave earlier, if your provider's DNS servers, LDNSs, are in geographically separate places from where your customer is, it's possible they would land on a different edge. So in the example I gave, if your DNS was served from Phoenix, we have an edge in Phoenix, it's going to go to that node. And then if you're in Seattle, when you actually go for HTTP, you're landing in the Westin. So there's not a correlation there. The answer is, although it's not guaranteed, it is good enough. So we see, when we scrape through the data, there's about an 80% correlation between where the DNS request lands and where the HTTP request lands. And there are some outliers based on ISP configuration. But in general, it's that. And the good news is, you only need to shed the percentage of traffic that you're overloaded. So if you're overloaded 10%, you can shed it. If you have 80% correlation, you can shed 80% of traffic. There's just 20% somebody else is giving out the DNS answer for, and you're getting that traffic. So this has been sufficient in the real world. And if you get a super huge spike that's just killing you, because it's Anycast, you just pull the node out of the way and let it go somewhere else. So here's, got 2 slides to go. Here's the actual slide of it working in practice. This is one of our services running. This is over a day. So you can see there's a couple of spikes at peak time for the day, which looks to be midnight UTC. I don't know where that is. And as the traffic load, this was just CPU at this point, crosses what you just decide is your operating threshold, the bottom graph shows that the amount of traffic that gets the second DNS answer ramped up to 30%. And we have done a lot of work here on the feedback algorithm. You want it to take a fairly strong first step in case it's a sudden event, but you don't want the traffic to bounce backwards and forwards between two, and we had some flapping initially. So we worked on those. And then again, it's during the day when it's quiet, you serve 100% of the traffic. Everybody's getting optimal performance. And then again, when the peak comes the next day, this time it wasn't quite as big. You just shaved off the amount of traffic you needed to be able to have each node operating at full efficiency. So in summary, we statically configured the edges into multiple Anycast layers, Anycast rings we call them. Each edge independently monitors its load, and if it gets too busy, it just, for some percentage, says, hey, guy behind me, you deal with it. We didn't want to shed across the same layer because you can get into oscillation there, that one node gives up traffic to the guy next to him, that edge then has too much traffic, gives it away, it might come right back to you. So we just go straight, it's up the chain of size, and in our world that's like back towards the center of the network. And the final layer, we assume, is dimensioned sufficiently to handle all load. In an Azure world, in an AWS world, you can dynamically scale now, so it is fairly simple to do that. And then my pitch at the end is to get the maximum benefit from Anycast does require a collaboration. We can't impact the inbound path from your customers to our servers at all. It's totally under your control. We're announcing the same routes to you from every point of presence we have. If you choose to send all the traffic, whoa, sorry everybody. send all the traffic to one location, then that location, your users will get slow performance, we'll handle it, we'll shed traffic. But in order to get the maximum performance here, having the customer's connection land on the server that is closest to the eyeballs is important. And that's it. Any questions? It's the exciting moment for me here. Hi.
Hi, Chris Woodfield with Twitter. A lot of us are now doing stuff, a lot of TCP over Anycast nowadays, and it does seem that different people that do it tend to have different solutions for the ICMP path MTU issue that inevitably comes up, where if you send a packet back to a client that would generate an ICMP error, the return error won't necessarily hit the same host, or even sometimes not even the same site where the server that generated that offending packet lives. Has that proved to be an issue for you? And if so, I'm curious what your solution to that has been.
Right. It's a great question. That has not. So I will find you later and ask to learn more about that. In general, I think we have an advantage. I was saying to some people earlier that your view of the internet is based on where you stand. Mm-hmm. So standing inside 8075, we have a consistent announcement from the edge sites of the network, regardless if one of my POPs goes up or down. As far as the internet is concerned, the address is still announced and the BGP is stable. So we see a super high correlation on very little route flapping, right? So I would expect that traffic to come back to the same server, but I'd love to hear some more details. Thanks for the question. Thank you. Yeah.
Philip Matthews, Nokia. I guess my question is actually perhaps even more basic than there, is that how much problems do you see with running TCP over Anycast? Because some years ago when I was doing some work in the IETF and had to do this, I got a lot of pushback from the various powers in the IETF about the idea of, the first packet might go to one server and the second packet might go to the second. And so it's a bunch of ideas like I got shot down by that. And so I'm curious, you're bringing in some real world experience, and it sounds like some others are too. How do you find this? Do you find the problem with, your first TCP going to one server and the second one? Do you guys try to measure that?
No, yeah, I can speak to that. So again, I think one of the advantages, or the way it's been easier where I stand, is having this global network, that the announcements to the internet are not flapping. But yes, we've been live now about 4 years with this gradually ramping the traffic, and we have had 3 instances where the traffic coming in has been a problem, and we've had a call for that. So it does happen. It's very rare. We have to reach out to the provider in that case. And it is exactly what you say. So we had an instance where we peered with a provider in Lynx and in AMSIX. We peered directly in AMSIX, and they just heard our routes through the route server in Lynx. And due to some network configuration on their side, they'd send alternating packets to one or the other. So we got the SYN in Amsterdam, and the server would respond with the ACK. That went through fine. They'd send the ACK to London, and the server receiving that would go, what on earth is this? Reset. It's very clear when you have a problem because it's completely broken for that ISP in that location. So there's no I'm not sure it's working right. It's busted. And during debugging of that, we figured out if they changed their source address, it worked fine. If they hit different destination addresses within the /24, some of them worked, some of them didn't. So it seemed to be a hashing problem on their side as to where it was going. And in general, you have to work with people because the inbound path, as I say, is not under our control at all. So yes, if someone sends it, alternating packet. So I think probably helped by everybody else, and the fact there are several big Anycast CDNs, people have been fixing those issues in their networks. So it's pretty rare, but it does happen. Yeah. So I think it would be great for someone to do a redo on how stable is Anycast, 5 years on. And I did see a paper that said for the larger providers, it is much more stable. If you only have a couple of spots in your Anycasting and you go up and down, that can have a big difference. But when we're announcing from 80 places around the world, it works well. Thank you.
Okay.
Hey, Peter.
Hey, Peter Labakov.
You're getting your own back because I asked you a question.
I know, Facebook. Question here, load shedding. I think previously we looked into using L4 load balancing to offload traffic from a POP two different POP. So how did you guys actually use that, or did it work out at all? Because right now it seems like it's DNS-based.
Yep. No, we are not
So it
using
has-
that currently. Yeah, so today, as I described, it's all DNS-based. There's a fascinating thought, as you say, that when the traffic comes into any edge node,
Right.
you could look, basically say, I've got that traffic, which is the best place behind me to serve it, and add another layer in. And we're investigating that, but it hasn't made it to production yet.
So
Yeah.
question is, you kind of have the same DNS problem, TTL expiration in this case, right? Which you described before. DNS has timeout issue. Like, you have to reduce TTL, all these things to be able to redirect traffic quicker.
Yes, that's true. So yeah, and when you add in the load shedding, so what we start to do with the DNS servers, as the load is rising, we start to drop the TTLs we're giving out, so some people
Okay.
are able to change direction more quickly. But yeah, there's a time period for
Reason
that
like,
changeover
okay.
based on TTLs. Yeah.
Okay, thanks.
Yeah, thank you. And then I guess last question, I'm about out of time.
Hi, Daniel Ryan with Max CDN. I just had a quick question on, you said you announced your Anycast networks globally. Do you see yourself running into issues with route leaking? And since the AS path might be the same, whether it's going to Asia or South America, and do you use any kind of GeoDNS, or is there some kind of something you do in the back end on your side to deal with this issue?
Yeah, so the question's on the route leaking. We have had one instance of that. So in general, we're leaky ourselves in that we're giving the same IPs out from 80 different internet locations. So there's a lot of cross-feed, and we just rely on BGP shortest path to answer that. We had one of the nodes we have that's embedded in an ISP that was leaking to the internet, and it pulled a lot of traffic to that location. That's totally possible. In general, when we announce the routes to an ISP location, that contractually, that's supposed to stay within their network. And so we have monitors, and if it starts to get too much load, too much traffic, then we just pull that location. Again, with Anycast, it's pretty easy to make changes. If something's gone wrong, just take it out, and the traffic will go to the next place. So yeah, those ones that have leaked, the one that has leaked the route, we just turned it off and then talked to them and got it fixed.
Thank you.
Thank you. Great, thank you, everyone.